Picture a thriving tropical forest. Stable ground, abundant resources, and an endless canopy of green. Now compare that to a coastal mangrove. Mangroves exist in an environment actively hostile to plant life. Their roots are choked of oxygen by aggressive tidal flooding, and they are forced to synthesize complex defense compounds just to survive the punishing salinity of the ocean. Yet this chart reveals a massive biological anomaly. If we plot annual carbon sequestration rates, an ideal terrestrial upland forest maxes out around 2.5 to 3.5 megagrams of carbon per hectare. The stressed, flooded mangrove captures between 6 to 8 megagrams, and that discrepancy multiplies when we look at the time frame of that storage. A standard terrestrial system typically cycles through its stored carbon every few decades. The coastal mangrove system holds its reserves intact well past 5,000 years. Standard models of tree growth and canopy density cannot account for this data. To understand this 3 to 5 times carbon multiplier, we have to look past the leaves. Mangrove trees do not necessarily grow faster than their tropical counterparts. Growth rate alone cannot account for the sequestration discrepancy. Instead, the blue carbon multiplier is a product of a radical shift in biogeochemical allocation and the specific decomposition mechanics of deep, submerged soil. To map exactly how this works, we need to compare these two ecosystems across 3 variables: the initial carbon inputs, the physical structures they build, and the chemical rate of decay at the end of the line. That requires shifting our observation away from the dense canopy above and forcing our perspective to descend deep into the waterlogged environment below ground. Evaluating the true climate value of a coastal ecosystem means unlearning our terrestrial biases about where a forest actually keeps its carbon. At the initial input stage, both upland forests and coastal mangroves share the exact same foundation. They capture atmospheric carbon dioxide through tiny pores on their leaves, called stomata. This equation represents the baseline conversion inside the leaves. Solar energy breaks apart carbon dioxide and water, forcing them to recombine into glucose. The plant uses that glucose to build complex structural chains, creating rigid wood and essential defense compounds. Ecologists measure out this total biological output using a metric called net primary productivity. This calculates the exact mass of dry, structural plant matter created in a single hectare over the course of a year. In terms of raw manufacturing, the mangrove system generates 8 to 12 tons of new dry matter per hectare annually. Since carbon makes up roughly half of that dry weight, this biological production directly translates into capturing between 6 to 8 megagrams of carbon out of the atmosphere. That is a highly efficient biological engine. But high productivity at the leaf level cannot fully explain how that volume of carbon becomes permanently locked away. The massive divergence in long-term storage happens at the next step, the strategic allocation of those physical building blocks. This graphic traces the physical carbon flow. A terrestrial forest directs 70% of its fixed carbon upward into above-ground biomass. The mangrove inverts this model. It forces up to 70% of its production directly downward into its dense root system. Biologically, this extreme below-ground allocation is a strict requirement for survival. Withstanding the relentless physical assault of tidal surges and unstable shifting mud requires massive anchoring infrastructure. But by building that underground anchor, the mangrove has inadvertently created a highly efficient carbon pump, routing the majority of its captured carbon away from the exposed surface entirely. While a tropical forest spends decades building a highly vulnerable carbon tower high into the sky, the mangrove functions as heavy industrial machinery, driving atmospheric carbon directly into the sediment profile. Pumping internal carbon underground is only half of the structural equation. To see the rest, we have to look at the external hydrology. Coastal zones are subject to a constant daily influx of tidal waters and riverine flows. These waters carry heavy loads of suspended silts and external organic matter flowing from further inland. When those swift currents hit the dense matrix of mangrove roots, the physical obstruction acts as a severe hydrological break, disrupting the incoming flow. As the velocity of the water drops, it loses the kinetic energy required to hold that material in suspension. Heavy particulates simply fall out of the water column and settle onto the coastal floor. This imported sediment forms a continuous protective layer over the mangrove's own fallen leaves, twigs, and propagules, effectively burying the local carbon before the receding tide can wash it out to sea. We can measure the exact result of this continuous trapping process. Mangroves achieve an average carbon burial rate of 174 grams per square meter every single year. The root system operates as an active, self-sustaining geological net. It traps imported carbon from the water and seals it tightly over the biological carbon pumped down from the leaves above. Below the mudline, the specific decomposition kinetics of the sediment profile finalize the carbon multiplier effect. In standard, dry terrestrial soils, abundant oxygen diffuses easily through the dirt. Soil microbes use that oxygen as fuel to rapidly and efficiently oxidize dead organic matter, returning it directly to the atmosphere as carbon dioxide gas. Mangrove habitats bypass this default decay cycle. The constant tidal inundation guarantees a deep soil profile that is permanently saturated with water, creating an entirely oxygen-deprived environment. This animation shows the precise chemical limitation at work. Oxygen diffusion is physically blocked by the water filling the soil pores, completely cutting off the standard fuel supply for those microbes. Stripped of their primary oxygen source, submerged microbes are forced into a difficult biochemical workaround. To survive, they switch to alternative electron acceptors like sulfates or iron to break down organic material. But this anaerobic chemistry is highly inefficient. That metabolic shift drops decomposition rates by 10 to 50 times compared to dry land. The coastal advantage goes far beyond the speed of photosynthesis. The mangrove leverages anaerobic chemistry to deliberately stall the biological decay cycle, trapping the carbon in a perpetual bottleneck. When you combine the aggressive below-ground allocation pumps, the hydrological sediment traps, and the anaerobic kinetic bottleneck, you are left with a profoundly flipped ecosystem inventory. This data table summarizes the final tally. In a mangrove system, 80 to 90% of the primary carbon storage is located permanently beneath the surface, deep within the soil. That is the inverse of the terrestrial forest, which leaves 60 to 70% of its captured carbon completely exposed in its living above-ground wood and leaves. We have physical proof of just how well this coastal storage model works. Scientists extracting undisturbed soil cores from mangrove mud regularly pull up dense carbon deposits that accurately date back more than 5,000 years. Evaluating the power of a mangrove by looking at its trees completely misses the point. The vast majority of its climate value is held in an invisible, deep geological reserve. Yet this efficiency creates a strict vulnerability paradox. The exact anaerobic water conditions that make this storage possible also constitute a massive point of failure. When humans impose structural land use changes on the coastline, specifically by trenching and draining the mangroves for commercial agriculture or aquaculture, the entire physical system is compromised. As the local water table is artificially dropped by those trenches, the seal breaks. Atmospheric oxygen rushes down into the previously protected 5,000-year-old anaerobic soil profile. This triggers an immediate kinetic cascade. The anaerobic bottleneck shatters in an instant, and the newly oxygen-rich microbes accelerate their biological oxidation back to maximum speed. When a terrestrial forest burns, it releases a few decades of accumulated carbon. When a mangrove soil is drained, the resulting microbial oxidation can release thousands of years of stored carbon back into the atmosphere in just a few short years. Effective climate mitigation depends on protecting the specific hydrological conditions that keep this millennial carbon vault safely sealed beneath the tide.